Imagine staring at a computer screen, and right there, sitting in a digital wallet, is $3 million.
Yeah, it's just staring back at you.
Right. You know the money is yours. It is a massive, life-changing fortune. But the password to actually get to it is locked in some corner of your brain that you haven't accessed in 11 years.
I mean, the anxiety of that would just be completely crushing.
Oh, I would absolutely lose my mind. And for over a decade, traditional brute force hacking, you know, throwing millions of combinations a second at the encryption, it just couldn't help this person.
Because the math is just too strong.
Exactly. The math is flawless. But last month, someone actually got that money back. And they didn't do it by breaking the cryptography at all. They did it by having an AI basically psychoanalyze their messy human memories.
Which is just a profound shift in how we have to think about digital security moving forward. I mean,
Right.
we spent the last 40 years building these impenetrable mathematical fortresses, right?
Yeah.
Assuming the walls would protect whatever we put inside. But we completely ignored the fact that the person holding the key is, well, incredibly predictable.
Welcome to this deep dive. Today, we are bringing you into the really fascinating and frankly kind of terrifying intersection where unbreakable cryptography collides with flawed human psychology.
And we're going to examine how artificial intelligence is just completely rewriting the rules of engagement here.
We have a great stack of sources for you today. We'll be looking at a developer's real-world account of that massive Bitcoin recovery.
Right, and then we're going to dig into a brand new academic paper on something called LLM-guided prompt evolution, which basically explores how AI is learning to guess passwords at a massive scale.
We're also pulling from a really comprehensive machine learning study on password strength detection. And finally, we're going to look at the technical documentation for an open-source Ethereum wallet toolkit.
Along with some heavy security research on vanity addresses that comes with it.
Okay, let's unpack this. Our mission today is to show you how the ultimate vulnerability in your digital life isn't the encryption algorithm. It isn't the math at all. The vulnerability is you.
Yeah, it's your memory.
It's your memory, your typing habits, and as we'll see later, even your literal eyeballs. We want to understand how AI is currently being weaponized as this ultimate lockpick to exploit those human flaws, but also how it might be our absolute best hope for a safeguard.
Because if the math isn't failing, but the human is, I mean, the only way to secure the system is to change how the human actually interacts with it.
Exactly. So let's jump right into the human element, specifically how we create and remember passwords in the first place. And I really want to go back to that $3 million wallet because this story is just wild.
It really is.
There's a user on X who goes by the handle CPRKRN, and they had 5 Bitcoin locked in a wallet since roughly, I think 2013 or 2014, just sitting there.
Which is an absolute eternity in the crypto space. I mean,
Yeah.
think about the anxiety of watching the price of Bitcoin fluctuate wildly over an 11-year period.
Oh, yeah.
Knowing you own a piece of it, but
Yeah.
you literally cannot touch it. It must have been completely agonizing.
Well, CPRKRRN finally recovered access, and they did it with the help of Claude AI. Now, when a story like this hits the timeline, everyone naturally panics, right?
Oh, instantly.
You see these headlines screaming, AI breaks Bitcoin. So let's just set the record straight right now. What actually happened here? Because, I mean, if AI can just casually reverse SHA-256 encryption, the entire global financial system is basically over tomorrow.
Right. Let's put that feud to rest immediately. Bitcoin uses the SHA-256 encryption standard.
Mm.
And to give you an idea of the sheer scale of that math, if you took every single computer currently operating on Earth
Okay.
and dedicated them entirely to guessing a 256-bit key,
Yeah.
you would literally be waiting until the universe experienced heat death before you found a collision.
Wow.
Yeah. AI did not break Bitcoin. It didn't find some secret mathematical backdoor.
So it didn't outsmart the math at all.
Not even a little bit. What the developer in our source material highlights is a process they call AI-assisted memory reconstruction. The user didn't ask Claude to crack a cryptographic hash. They handed the AI a digital box of personal junk.
I love that framing. It's like a digital box of junk you'd find in the attic.
Precisely. They provided an old seed phrase, some forgotten text notes, old wallet files, and just these vague, fragmented memories of what their password habits used to be a decade ago.
Right.
So the AI didn't attack the cryptography. It analyzed the human. It connected the psychological dots.
And the source material provides this brilliant, sanitized C# demo to show exactly how this works under the hood, without exposing anyone's real private keys.
Which is important, yeah.
The developer fed an open source LLM They used Kimi or Olama for this, some really vague clues. They fed it the words memory and police, a note mentioning the year 2014, an instruction to combine memory and police, a hint about an underscore format, and just a random note saying BTC price 230.
And that is just a perfect example of how human memory degrades over time. I mean, we don't forget everything uniformly, right? We remember the emotional anchors.
Yeah, exactly.
A favorite movie, a significant year, a specific financial milestone, like the price of Bitcoin at that exact moment.
But if you feed those fragments into a traditional brute force password cracker like Hashcat, I mean, what does it actually do?
It fails miserably. Because traditional brute forcing is fundamentally blind to context. A standard dictionary attack will just try every single word in a text file.
Yeah.
And a pure brute force will just cycle through permutations. A, B, C, then A, B, A, C.
Right.
It doesn't know what memory or 2014 actually signifies to a human being. It just treats them as meaningless character strings.
But the LLM processes it entirely differently. In the demo, the LLM didn't just spit out a random jumble of letters and numbers like a capital B $3 sign KL9.
No, not at all.
It generated a ranked list of human plausible candidates. The number one guess was memory underscore police underscore 2014. Number two was police underscore memory underscore 2014.
It even tried memory underscore police underscore 230 based on that Bitcoin price clue. It basically turned messy personal history into a ranked list of highly likely hypotheses.
And why is it so good at that?
Well, the underlying mechanism here is fascinating when you look at the machine learning study on password strength detection we have in our stack. The LLM is leveraging its latent space.
Meaning its understanding of language.
Right, its massive understanding of human semantics. Humans just don't act like random number generators. We are highly structured creatures. We build passwords based on syntactic rules. Noun underscore noun 4-digit year. The LLM understands that grammar natively.
So it's not really guessing the password at all. It's predicting the human who made the password, which feels less like a mathematical attack and more like a digital Sherlock Holmes.
That's a great way to put it.
Right. Imagine someone walks into your messy bedroom. They look at the movie posters on your wall. They see your high school yearbook on the desk. They notice you have a dog. And instead of trying every single key blank in a factory to open your safe, they just say, well, the combination is your dog's name and the year you graduated.
That is an excellent analogy.
Yep.
You completely bypass the infinite mathematical key space, and you confine your search to a highly restricted psychological key space.
Yeah.
The encryption is still perfectly intact. The vulnerability is just that the human setting the lock couldn't generate true randomness.
Which brings up a massive privacy warning that the developer explicitly highlighted in the source. If you are listening to this right now and thinking, great, I'm going to dump all my old hints into ChatGPT to recover my old MySpace account, you really need to stop.
Yes, absolutely. Do not upload your real seed phrases, actual private keys, or raw wallet files to any cloud-based AI model, because when you upload that context to a commercial API, it is processed on a third-party server.
You are literally handing the digital Sherlock Holmes the keys to your entire life.
Exactly. The developer strongly advises that if you absolutely must use an LLM for recovery, you have to sanitize your hints. Abstract them entirely.
Like what?
Don't say, my dog is named Buster. Say, common male dog name. Or, better yet, run a local offline model on your own hardware so the data never even leaves your physical room. Because if an AI can reconstruct your password from just a few vague concepts, you are leaking your entire cognitive footprint.
Wow. Okay, so that is the feel-good story, right? AI acts as a digital therapist, helps a user remember their password, and saves the day. But let's flip the script here. Because if AI can do this for good, what happens when malicious actors decide to automate this exact contextual guessing at an industrial scale?
Well, this is where we cross from theoretical risk into active scaled weaponization.
Yeah. We have this Archic paper titled LLM-Guided Prompt Evolution for Password Guessing. And this isn't about an AI helping one guy recover a specific wallet. This is about an AI systematically learning how to guess human passwords better, completely on its own, without any human intervention.
Let's break down the architecture of the attack they built here, because it is incredibly sophisticated. The researchers basically combined two systems. First, an evolutionary algorithm framework called OpenEvolve, and second, a large language model guesser called PassLLM.
And PassLM is really crucial here, right? Because it was fine-tuned on the RockU dataset.
Yes, the infamous RockU breach.
Wait, I actually need to push back on this for a second. The RockU breach happened in, what, 2009?
That's about right, yeah.
It exposed 32 million plain text passwords, but that was over 15 years ago. If PassLLM is training on a database from 2009, isn't it just learning how to guess completely outdated passwords? I mean, every single website today forces you to use a capital letter, a number, and a special character. People don't just use password 123 anymore.
That is a very common assumption. But the machine learning study in our sources proves it's actually a complete fallacy.
Really? Why is that?
Because forcing a human to add a symbol doesn't make them random. It just makes them predictably compliant. When a website demands a capital letter, 90% of humans just capitalize the very first letter of the word.
Oh, guilty as charged.
Right. When it demands a number, they slap a 1 or maybe their birth year at the absolute end. When it demands a symbol, they add an exclamation point at the very end.
Oh, wow. So the word monkey just becomes capital M monkey, 1 exclamation point.
Exactly. The syntactic structure of how human brains assemble strings hasn't changed at all since 2009. We just added arbitrary suffixes to the end. And PassLLM understands that underlying grammar perfectly. Now, the goal of the researchers here was to execute a trawling attack.
Let's define that for the audience real quick.
Sure. A trawling attack is a mass-scale attempt against a huge database of hashed passwords. The attacker has a very strict budget. Say, they're only allowed 20,000 guesses per account before the system permanently locks them out.
Okay.
So they need to maximize how many accounts they can crack within that incredibly tight constraint.
And in previous research, the creators of PassLM assumed that the prompt, the actual text instructions you type to tell the AI to generate passwords, they thought it didn't really matter that much.
Yeah, they assumed you could just prompt the AI with generate 100 common passwords and you'd get peak performance. The underlying training would do the heavy lifting.
But this new paper just obliterates that assumption. They proved that the prompt matters immensely, but instead of having human engineers sit around in a room trying to manually write better prompts, they used AI to iteratively rewrite and evolve its own prompts.
The AI is literally coaching itself on how to be a better hacker.
How does that even work mathematically? It sounds like sci-fi.
The OpenEvolve framework uses a concept borrowed straight from biology, genetic algorithms. Specifically, an MA Elite's quality diversity search paired with an island population model.
Okay, let's translate that for everyone. Islands and elites. What does this actually mean in terms of code?
Think of 3 separate, completely isolated laboratory environments. These are your islands. On each island, you have an AI generating passwords based on a specific prompt. The framework then grades those passwords based on 3 specific dimensions: complexity, diversity, and length.
So isn't just looking for one master prompt to rule them all, it's grading them in specific categories.
Right. That is the quality diversity aspect of it. It keeps the top performing prompts in each category. Those are the elites. Now here is where the LLM mutator comes in. It takes an elite prompt, analyzes its semantic meaning, and creatively rewrites it to see if a variation performs better.
It mutates the instructions.
Yes. And the islands. Every 10 iterations, these 3 independent islands pause what they're doing, and they exchange their best prompts. They cross-pollinate.
That is brilliant, because if Island A discovers this amazing instruction for generating, say, corporate-style passwords, and Island B discovers a really great trick for generating complex symbol patterns, they just share the knowledge. It prevents the AI from getting stuck in an evolutionary dead end.
Exactly. And the results they got were terrifying. The baseline unevolved prompt had a cracking success rate of 2.02%.
Which, I mean, out of 1 million leaked hashes is still 20,000 compromised accounts. That's a lot.
Yes. But after 100 generations of this self-directed evolution, the cracking success rate surged to a peak of 8.48%.
Wow. That is a 4 times improvement, just from the AI changing the words it uses to talk to itself.
And we have to look at how the generated passwords actually changed. The researchers use a metric called the per-symbol F-score.
What does that actually measure in practice?
It analyzes the character frequency distribution. It looks at the rhythm of the characters themselves. Do these generated passwords statistically match the deep unconscious typing habits of real humans? And the evolved prompts produce passwords that saw a 26% improvement in the area under the curve for this metric.
Meaning the AI wasn't just throwing random dictionary words at the wall anymore. It was statistically mimicking human behavior. It learned the exact mid-frequency characters we use. It completely mapped our cognitive footprint.
It learned how to think like us just by iterating on the instructions.
But here is the question that always comes up when we talk about this level of AI computation. To run an evolutionary model with 3 islands, cross-pollinating over hundreds of generations, grading millions of hashes. I mean, don't you need an absolute supercomputer for that? Like an NSA-level server farm?
That is perhaps the most critical, alarming detail in the entire paper. You do not.
Wait, really? You don't need a supercomputer?
No. The researchers ran an ablation study that did a relatively small, local, offline model, an 8 billion parameter model called Quen 3.8b, and they ran this entire evolutionary attack framework on a single consumer-grade GPU.
Are you serious?
An NVIDIA card with 24 gigabytes of VRAM, the exact kind of graphics card you could buy at a retail computer store right now.
Wait, a gaming computer?
A high-end gaming computer, yes. And the success rate. The massive cloud ensemble achieved an 8.48% crack rate. The single consumer GPU achieved an 8.28% crack rate.
That is a rounding error. They are basically identical.
The performance gap is entirely negligible, which means highly sophisticated, context-aware, evolving AI password cracking is completely democratized now. It is within the reach of a teenager in their bedroom, a rogue insider at a company, or a sophisticated syndicate. And because it runs locally, offline, it is entirely invisible to cloud API monitors. Nobody knows you're running it.
That completely upends the threat model. I mean, if AI acts as a digital Sherlock, but also mutates like a virus to hack us, what is the defense? What do we even do?
The research indicates that traditional password complexity rules are just dead. The AI models that behavior perfectly now. The only thing that currently slows this down is proactive restriction, specifically strict password policies that completely block any password string that has ever appeared in a known leaked database.
Because if the AI relies on the underlying patterns found in historical leaks, you have to force humans out of those historical patterns entirely.
Right. You degrade the attacker's fitness signal. You make it much harder for the evolutionary algorithm to know if its mutations are actually successful. But even then, the researchers noted that the most significant gains in cracking rates occurred in just the first 1 to 10 iterations. The AI adapts incredibly fast.
Okay, so let's follow the logic here. Human psychology is utterly compromised. We are just too predictable. Our memories are flawed. Our typing habits are an open book to machine learning. If the human is the vulnerability, the logical solution is to remove the human entirely. We should just let machines generate perfectly random cryptographic strings for us, right? Just let the math do the heavy lifting.
Well, in theory, yes. If human entropy is low, you rely on machine entropy.
In theory. But our next source shows us exactly what happens when the machines get their randomness wrong, and it is a catastrophic disaster. Let's dive into the Ethereum Wallet Toolkit documentation, specifically their research on vanity addresses.
This is one of the most painful, expensive lessons in the history of applied cryptography.
Let's set the stage for anyone listening who isn't deep in Web3 infrastructure. What exactly is a vanity address?
When you create a cryptocurrency wallet, the cryptography generates a random public address. It's a long hexadecimal string starting with 0x. To a human, it's just visual gibberish. A vanity address is a custom string where someone has used specialized software to rapidly generate millions of private keys until it randomly spits out a public address that contains a specific, recognizable pattern.
Like 0x bad boy or something that starts with a bunch of zeros. But why do people do this? Is it just flexing?
There's a branding element, sure. If you are a major protocol, you want users to visually recognize your smart contract so they don't get scammed. But there is also a massive hidden financial incentive on the Ethereum network specifically.
This blew my mind when I read it in the sources.
Yes. According to the Ethereum Yellow Paper, the transaction data structure actually penalizes non-zero bytes. It costs more gas, which translates to real money, to process a transaction if the address contains a lot of random characters. Conversely, leading zeros take up less computational space.
So the blockchain actively rewards you with cheaper fees if your address starts with 0x0000.
Precisely. And at the scale of a major institutional trader, that really adds up. Our sources note that a major crypto market maker, Wintermute, purportedly saved around $15,000 in gas fees simply because they used a vanity address with leading zeros.
Okay, so there is a real business case for it. You want to save money, so you download a vanity address generator. And for years, the most popular open source tool for this was a program called Profanity.
Profanity was beloved because it was incredibly fast. It utilized GPU acceleration to grind through hundreds of millions of cryptographic combinations per second. But Profanity harbored a fatal flaw in how it generated its randomness. This flaw became a massive CVE vulnerability.
Let's talk about the real-world impact before we get into the math. Because of this flaw, Wintermute, the same firm saving money on gas, was hacked for $160 million. Gone.
Just vanished.
And another project, Index Finance, lost $16 million. And there is a deeply ironic twist here. The attacker who drained Index Finance used a vanity address starting with 0xb5ed base dual to execute the hack. And then that attacker got hacked by a different attacker who exploited the exact same profanity vulnerability. It was a complete shark-eating shark scenario.
It was an absolute feeding frenzy on the network. And the root cause of all of this comes down to a pseudo-random number generator algorithm called MT19937.
Okay, MT19937. It sounds like a serial number for a spaceship part. What is it, and how did it fail so badly?
Well, MT19937 stands for the Mersenne twister. It is one of the most widely used pseudo-random number generators in classical programming. But we need to understand how computers actually generate randomness. A computer is a deterministic machine. It cannot roll physical dice. To create a sequence of random numbers, it needs a starting point, which we call a seed.
So it takes the seed, applies complex math, and spits out a chaotic-looking result.
Exactly. It twists the state. Now, a secure Ethereum private key must be 32 bytes long to provide sufficient cryptographic security. But the developers of Profanity made a critical error in how they seeded the Mersenne twister. They used a 4-byte seed.
A 4-byte integer, a d-int32.
Yes. And because they only had a 4-byte seed to start with, the software essentially had to stretch and stitch the outputs together to try and build a full 32-byte key.
How does using a 4-byte seed physically restrict the math, though?
It drastically reduces the key space. Think of key space as the total number of possible combinations. A truly random 32-byte key has 2 to the power of 256 possible combinations. As we said earlier, that is practically infinite. But because Profanity's entire generation process was downstream of a 4-byte seed, the actual number of unique private keys it could ever mathematically generate was reduced to 2 to the power of 32.
And what is 2 to the 32nd power in plain numbers?
Roughly 4.2 billion.
4.2 billion, which, I mean, sounds like a big number to a human being, but what does that mean to a GPU?
To a modern graphics card, 4.2 billion is nothing. It is trivial. Attackers realized that every single private key ever generated by the Profanity tool belonged to this tiny pool of 4.2 billion possibilities. So they didn't even need to attack the blockchain directly. They just rented some cloud servers, ran the Mersenne twister algorithm forward for all 4.2 billion seeds, generated the corresponding public addresses, and saved the entire list to a hard drive.
Wow, it's basically a master keyring?
It took less than 2 terabytes of storage. They pre-computed the entire universe of Profanity addresses.
I want to make sure you listening really visualize this. What happened here is like you bought a massive state-of-the-art titanium vault, and the manufacturer boasts that the lock has 1 trillion possible combinations. The math is sound. But what you don't know is that the lazy factory worker programming the locks only ever used the numbers 1 through 5 for every single vault that rolled off the assembly line. The vault itself is unbreakable, but the creation of the lock was entirely compromised. And anyone who knows a factory worker's secret can just walk up with a small list of 5 combinations and open your titanium vault.
That is exactly what happened. The attackers had the master list. They simply scanned the Ethereum blockchain, looking for high-value accounts that had vanity addresses. When they spotted Wintermute's vanity address, they did a quick lookup in their 2-terabyte database, found the corresponding private key, and just authorized a transfer of $160 million.
Unbelievable. So what is the takeaway here? Should you just never use a vanity address under any circumstances?
You can, but you must understand the architectural difference between account types on Ethereum. There are externally owned accounts, or EOAs, which are regular wallets controlled by a private key, and smart contract accounts, which are controlled by code.
The documentation quotes a well-known Web3 developer who goes by Foobar. He said, EOA vanity is the road to bankruptcy. Smart contract vanity is the road to success. Why is there such a stark difference?
It comes down to what you are actually generating. When you use a vanity tool for an EOA, you are generating the private key itself. If the randomness is flawed, the key is known and your money is gone. But when you deploy a smart contract, you use an Ethereum opcode called create2.
How does create2 work?
Create2 determines the final public address of a contract by hashing 3 things: the creator's address, the contract's bytecode, and a salt. A salt is just an arbitrary number you choose.
So to get a vanity address for a smart contract, you just keep guessing different salts until the math spits out a public address you like.
Exactly. You are grinding to find a public salt, not a private key. The salt is public information. It gets broadcast to the entire network.
Yeah.
Even if an attacker knows exactly how you generated your salt, it doesn't compromise the contract because there is no private key attached to a salt. The security relies entirely on the smart contract code, not on keeping the generation process secret.
Okay, so if you need a regular wallet, an EOA, do not touch vanity generators. Do not try to make the math look pretty. You have to rely on cryptographically secure pseudo-random number generators, the OSCSPRNG, things like dev/urandom on a Linux system, which pull from chaotic system noise like fan speed variations and thermal fluctuations to generate true unpredictability. The official libraries and the Ethereum toolkit use these secure sources. Let the machine be truly random.
Right. Never compromise entropy for aesthetics. It is never worth it.
Okay, so we've established that human memory is a vulnerability because AI can guess it. We've established that machine generation can be a vulnerability if the randomness is lazy. But let's play devil's advocate for a second. Let's say you do everything perfectly. You don't use a memorable password. You use a hardware wallet with true cryptographic randomness. You never use a vanity address. Your math is absolutely bulletproof.
You are still profoundly vulnerable.
Why?
Because an attacker doesn't need to break your math. They just need to hack your visual perception.
This brings us to a section of the security research that is genuinely unsettling. It relies entirely on a physiological flaw in how human beings process information. We are talking about address poisoning.
Think about what happens when you look at a typical blockchain address on your screen. What is your brain actually doing?
Well, I see 0x followed by a massive wall of 40 random numbers and letters, and honestly, my eyes just glaze over. I cannot hold a 40-character hex string in my working memory. Nobody can.
And that cognitive limitation is exactly the attack vector. Human brains rely on visual heuristics, mental shortcuts, to process complex information quickly. We don't read every letter in a word. We recognize the overall shape. When a crypto user goes to verify an address before sending funds, their brain naturally performs what is called a saccade, a rapid eye movement. They check the first 4 characters, jump to the end, and check the last 4 characters.
Right. I say, okay, it starts with 0XABCD and ends with 5678. Looks good to me.
Yes. If the start and the end match, the brain automatically, subconsciously assumes the chaotic middle section matches as well.
And attackers exploit this biological shortcut. Let's walk through exactly how an address poisoning attack works in the wild.
First, the attacker monitors the public blockchain ledger. They use automated scripts to watch your specific transaction history. They notice that you frequently send large amounts of USDC to a specific counterparty. Let's say it's your own cold storage vault.
Okay, so they know I send money to my vault every Friday.
The attacker takes the public address of your cold storage vault and they run it through a vanity address generator. Ironically, very similar to the jewels we just discussed. But they are looking for a brand name. They are running the generator to find a lookalike address. They grind combinations until the software spits out an address that perfectly matches the first 4 and the last 4 characters of your legitimate vault.
So my real vault is 0xABCD, random middle 5678. The attacker generates an address that is 0xABCD, entirely different middle controlled by the attacker, 5678.
Exactly. Now they possess an address that will pass your visual heuristic check. The next step is the actual poisoning part. The attacker sends a transaction from their malicious lookalike address to your active wallet.
But why would they send me money?
They don't send you real money. They initiate a zero-value token transfer. Many ERC-20 token smart contracts permit a user to transfer an amount of 0. Alternatively, they might use a spoofed fake token contract to make it look like you initiated a transaction to the lookalike address. The goal is not to drain your wallet directly at this stage. The goal is simply to force their lookalike address to populate in your wallet software's recent transactions history.
Wow. They're literally planting a landmine in my user interface.
Yes. So Friday rolls around. You open your wallet app to send funds to your cold storage. You don't want to type out a 40-character hex string, so you go to your recent transaction history. You see an address. Your brain does the visual check. Starts with ABCD, ends with 5678.
I assume it's my vault, and I just click copy.
You paste it into the destination field, you authorize the transaction, the cryptographic math executes perfectly, and your funds are instantly sent to the attacker.
And this isn't theoretical. This is happening in the wild right now. Our sources highlight a devastating incident from May 3rd, 2024.
It was a catastrophic success for the attackers. A single victim was targeted by a poisoned address. They copied the wrong look-alike string from their history, and in one click, they lost 1,155 wrapped Bitcoin.
1,155 wrapped Bitcoin. That was roughly $72 million at the time of the attack, lost because of a visual typo. How is it possible that an infrastructure built on absolute mathematical certainty can be completely undone by someone sending $0 to a wallet? Why didn't the blockchain stop it?
Because the blockchain functioned exactly as designed.
That is a terrifying answer.
But it's true. The network received a valid transaction. The cryptographic signature provided by the user was mathematically perfect. The consensus layer verified that the user had the funds and authorized the transfer. The failure did not occur at the protocol layer or the cryptography layer at all. The failure occurred entirely at the human-computer interface layer. The system blindly trusted that the human had visually verified the 40-character string.
Which we just established humans are physiologically incapable of doing reliably.
The crypto space has a massive, unacknowledged reliance on visual recognition of hex strings. The source material references an academic study from UC Santa Barbara to illustrate this. The researchers wanted to map the Ethereum arbitrage ecosystem. They wanted to identify all the decentralized exchanges, or DEXs, operating on the network over a 28-month period.
How did they find them? Did they scrape the smart contract bytecodes?
They did utilize some behavioral analysis, but a significant portion of their methodology actually relied on visual heuristics. They looked at vanity labels and Etherscan tags. They identified over 50,000 addresses as DEXs, largely through visual attribution. Even at the highest levels of academic research, humans have to rely on visual tags and labels because raw hexadecimal is just completely opaque to human cognition.
So we are swimming in an ocean of mathematical complexity using meat-based hardware that just isn't built for it. Our memory is a vulnerability. Machine generation can be a vulnerability. Our physical eyeballs are a vulnerability. If we can't trust our brains or our eyes, how do we survive this?
We need an abstraction layer. We need a secure intermediary that handles the perfect math without relying on our flawed perception. And ironically, the very technology that hackers are using to crack our passwords, artificial intelligence, is providing the blueprint for that secure intermediary.
This is where we get to the final piece of the puzzle today, AI as a defense mechanism. Let's talk about the Ethereum wallet toolkit documented in our sources. Because this isn't just a standard piece of software, it's designed specifically as an MCP server.
Yes, MCP stands for Model Context Protocol.
I feel like MCP is the buzzword of the year in developer circles right now, but what does it actually mean for the everyday user?
Historically, interacting with an AI like Claude or ChatGPT meant typing text into a browser window and getting text back. It was completely isolated. The AI couldn't act on your behalf. MCP is an open standard that changes that architecture entirely. It allows an AI assistant to securely connect to external tools, APIs, and local data sources.
So it breaks the AI out of the chat box.
Exactly. With MCP, you can give Claude permission to execute specific actions on your local machine. The Ethereum Wallet Toolkit acts as a secure bridge. It allows the AI to understand and safely manipulate complex Ethereum cryptography.
And the documentation emphasizes that this runs locally and offline, which immediately addresses the massive privacy warning we discussed back in Section 1.
That is the critical security boundary here. The toolkit runs locally on your device. When the AI needs to generate a wallet or sign a transaction, it isn't sending your private keys up to Anthropic's or OpenAI's cloud servers. The AI orchestrates the command, but the sensitive cryptographic math executes in a secure, local Python sandbox.
So what specific capabilities does this toolkit give the AI? What is the AI doing that I shouldn't be doing manually?
It handles the deeply unforgiving operational security tasks. For instance, the secure generation of BIP39 mnemonics, your 12 or 24-word seed phrases. It manages complex hierarchical deterministic or HD wallet derivations.
Right, derivation paths. Things like M/44 prime/60 prime/0 prime/0/0. You see those strings buried in the advanced settings of wallet apps all the time.
And humans should never be manually typing those. One typo in a derivation path, and your wallet generates a completely different set of addresses, and you think you've lost all your funds. The AI natively understands the BIP44 standard. It knows that Ethereum operates on coin type 60. It can navigate that mathematical derivation tree flawlessly without human transcription errors.
The toolkit documentation also highlights its approach to key store v3 encryption. It specifically mentions supporting script and PBKDF2 key derivation functions. Why is it calling out script specifically?
This loops right back to our discussion about the profanity hack and the power of consumer GPUs. A key store file is an encrypted backup of your private key. If an attacker gets your key store file, they will try to brute force the password protecting it. Script is what cryptographers call a memory hard function.
Meaning it requires a lot of RAM to compute.
Exactly. It is deliberately designed to be computationally slow and require significant memory resources. This makes it incredibly hostile to attackers trying to use hardware accelerators or ASIC chips to run billions of guesses a second. PBKDF2 is an older standard. It's faster, which paradoxically makes it weaker against modern GPU arrays. The toolkit defaults to script to ensure that even if your file is exposed, the AI has protected it with the most aggressive mathematical friction available.
Again, it abstracts the complex security decisions away from the user. But there is one feature in this toolkit that I think is the absolute silver bullet for the visual hacking we talked about, and that is its support for EIP 712.
Data signing. I would argue this is the single most important interface upgrade in the history of Web3 security.
Let's explain why this matters. Because historically, signing a crypto transaction felt like walking into a dark room and signing a blank contract.
That is exactly what it was. Before EIP 712, if a decentralized application wanted you to authorize an action, your wallet would pop up displaying a raw, unformatted hexadecimal string, a wall of 0x garbage. The average user had absolutely no idea what they were signing. They just blindly clicked approve and hoped the app wasn't malicious.
Which is how phishing attacks flourished. People thought they were signing a harmless login request to a new game, but the hex string they actually signed was a highly specific instruction authorizing a malicious contract to drain every NFT out of their wallet.
Because the human couldn't read the hex, they relied on trust. EIP 712 solves this by replacing the blind hex string with structured, human-readable data. It forces the protocol to itemize exactly what is happening. Your wallet interface will clearly display you are signing an ERC-20 permit. You are granting address X the right to spend 100 USDC. This permission expires at midnight.
It provides a literal cryptographic receipt, and the MCP toolkit allows the AI agent to read, generate, and validate these EIP 712 structures perfectly.
Furthermore, it validates the domain separator.
Let's define the domain separator for a second.
The domain separator is a cryptographic context layer. It binds your digital signature to one specific smart contract on one specific blockchain network. It mathematically hashes the contract address, the chain ID like Ethereum managed versus Polygon, and the name of the application. The AI checks this domain separator to ensure that a signature you generate to trade on Uniswap on Ethereum cannot be intercepted by an attacker and replayed on a completely different network.
It completely mitigates cross-contract replay attacks. The AI basically acts as your localized, tireless cryptographic auditor. It checks the domain, it verifies the data types, it double-checks the hex addresses, it performs all the rigorous visual and mathematical validation that the human brain simply isn't wired to do.
It creates a trusted execution environment between the human intent and the cryptographic math.
So, if you are listening to this, the takeaway is massive. The era of, well, raw dogging cryptography is coming to an end. Think about how we use the internet today. You don't manually calculate your own HTTPS handshakes when you load a secure web page. You don't type in raw IP addresses, you use domain names. In the very near future, you will not be manually verifying 40-character hexadecimal strings or handwriting 24-word seed phrases on pieces of paper. You will have a localized, secure AI agent doing the cryptographic heavy lifting for you.
It is the only logical evolution. We built financial systems with perfect mathematical certainty, but we failed to build interfaces that accommodate human fallibility. AI bridge toolkits are the missing interface layer.
Let's recap the incredible journey we've been on today. We started by exploring how a localized AI, acting as a digital archaeologist, was able to reconstruct a user's fractured memories to recover a $3 million lost Bitcoin fortune. It succeeded not by breaking the encryption, but by understanding human semantic patterns.
Then we looked at the weaponization of that capability. We examined how large language models, utilizing genetic algorithms and cross-pollinating island models, can iteratively evolve their own prompts to crack human password habits with 4 times the efficiency, and all of it running on a standard consumer graphics card.
We explored the catastrophic failures of removing humans and relying on flawed machine randomness, detailing how a simple 4-byte seed bottleneck in the profanity generator led to an attacker pre-computing a master list of private keys, resulting in $160 million in stolen vanity addresses.
We analyzed how attackers exploit our biological limitations using address poisoning, successfully tricking a user into sending $72 million to a look-alike address simply because the human visual cortex relies on flawed heuristics.
And finally, we saw how AI is stepping in to secure those physiological gaps. Using the Model Context Protocol and structured EIP 712 data to abstract the raw hex away from our eyes, managing the complex derivation math so we don't have to.
If we synthesize all of this, the failures of human memory, the vulnerabilities of our visual perception, and the rapid evolution of AI agents, it leaves us with a truly fascinating, perhaps provocative question.
Oh, I love a good provocation. Lay it on us.
If AI can perfectly map our cognitive habits to crack our passwords and simultaneously navigate complex cryptographic boundaries to protect us from our own visual mistakes, are we rapidly approaching an era where the human element is completely removed from authentication altogether?
Wait, removed completely?
Yes. Imagine a near future where you never create a password again. You never write down a seed phrase. You never even see a raw wallet address on a screen. Instead, your personal localized AI agent autonomously authenticates with other AI agents via protocols like BY402. They conduct trustless commerce, verify your identity, and negotiate permissions entirely in the background. We have spent decades trying to teach humans how to safely hold cryptographic keys. But the safest system, it turns out, might be one where humans simply aren't allowed to touch the keys at all.
Wow. We started this deep dive talking about the murky, unpredictable intersection where perfect cryptography meets the messy human brain. And it seems the only way to finally secure that intersection is to remove the human from the equation entirely. That is a massive paradigm shift to mull over. Thank you so much for joining us on this deep dive into the limits of human cryptography. Stay curious, stay secure, and we'll see you in the next one.